Next problem, y prime would be, bring the power down, so that's 3x, subtract 1 from the power, minus half of 6 is 3x to the negative 1/2. I missed the first part actually. Keep in mind those stands for radical. So that's the square root of x cubed, that's the square root of x. Domain, x is bigger than or equal to 0. Intercepts. If I set x equal to 0, I'll get y equals 0. And if I set y equal to 0, I could factor a 2x to the 1/2 out. I will have x cubed. Let me think. I'll get x to the 2 over 2, which is 1 minus 3. So I'll get 0, 0 again, it's already listed up there, 3, 0. So the graph passes through those points. I have intercepts already at 0, 0 and at 3, 0. Alright, now I go for my first derivative test. If I take a derivative, that's what it is. Where does that equal 0? Factor 3x to the negative 1/2 out. 3x to the 1/2 divided by, so the 3's cancel out. 1/2 minus a negative 1/2 is 1 minus 1. So I have x equals 0 and x equal 1 as critical points. X equals 0 and x equal 1. Remember, x cannot be negative, so I have to test, say, a half. If I pick a half as a test point right there, this is positive. 1/2 minus 1 is negative. And if I pick 2, that's always positive. 2 minus 1 is positive, so the function is decreasing and increasing. I have f is decreasing from 0 to 1. F is increasing from 1 to infinity. That indicates we have a local minimum at 1, and we plug that in the original equation. 2 minus 6 is a negative 4. So 1, negative 1, negative 2, negative 3, negative 4. A minimum. Second derivative test, I'll take y double prime, that is 3/2 x to the negative 1/2 plus 3/2 x to the negative 3/2. So if I set that equal to 0, I'll factor 3/2 x to the negative 3/2 out. I'll have x to the positive 2 over 2, which is x plus 1. So I have x equals 0 and x equal negative 1, but that's not part of the domain. So I only have 0 to worry about. Y double prime, and there's y. If I pick a point, say 1, that's always positive because the square root. 1 plus 1 is positive. That means f is concaving up from 0 to infinity. So the graph looks like this. Versus if I had it concave down to the right of that point, the graph would have looked like this. So concave up, and a point, it would have concaved down. But since it's concaving up all over, that's really what it looks like. Next problem is a fraction. Well, I could get around that. The third time would be a charm. Okay, it's not accepting. Back. There, got it. Okay. Here I could get around the quotient rule by saying, well, y equal x squared minus 1 to the negative 1. Take it. Again, I'm getting too excited. Domain. All reals except x equaling plus or minus 1. Intercepts. If I let y equal 0, I'll get negative 1. There are no x-intercepts, so let me label what I have. I am aware that there are two vertical asymptotes, one at 1. So here I'm going to expand that a bit, and I'm going to say that's a 1 and that's a negative 1. The limit as x approaches infinity of 1 over x squared minus 1 equals 0. Asymptotes help out with the graph. Now I go for my intercepts. Well, the graph passes at the point 0, negative 1. Okay, that's what I have. Now the derivative of this is actually bring the power down, subtract 1 from the power. So in reality it is negative 2x divided by x squared minus 1 squared. I have 3 points to worry about. Where does the derivative equal 0? That's when x equals 0, the top of the fraction equals 0. And where does the derivative not exist? That's when x equals plus or minus 1. So negative 1, 0, and 1. There's my y prime, there's my y. Pick a point to the left of negative 1, say negative 3. The denominator is squared, that means it's always positive. If I pick negative 3, the top, negative 2 times negative 3 is positive. A point in between negative 0 and negative 1, say negative a half, negative 1/2 times negative is also a positive. And if I pick a positive point either here or here, negative 2 times the positive will be a negative. So there it is. I have a function that's increasing, then decreasing. So f is increasing from negative infinity to negative 1, union with negative 1 to 0. F is decreasing from 0 to 1, union with 1 to infinity. It seems I have a local maximum at 0, negative 1 in the original, of course. So this is a maximum. It looks like that. Now I'm going to go for concavity. And concavity has to deal with the second derivative. So y prime equals negative 2x times x squared minus 1 to the negative 2. Y double prime, derivative of the first times the second, plus the first, derivative of the second, bring the power down, subtract 1 from the power, times the derivative of the inside. So if I factor a negative 2 into x squared minus 1 to the negative 3, this divided by this will give me x squared minus 1. This divided by this, the negative 2 disappears. And this disappears. So I'm left with negative 2x times 2x, which is minus 4x squared. So this is really y double prime is actually negative 2 times negative 3x squared minus 1 over x squared minus 1 cubed. Again, where does the top equal 0? Well, these are all positive, right? The top can never be 0. Where does the bottom equal 0? At 1 and negative 1. There's y double prime. If I pick negative, the top is always positive. If I pick negative 2, negative 2 is 4 minus 1, that's positive. If I pick 0, that's going to be, denominator will be negative. And if I pick point to the right, it's positive. So y is concaving up, concaving down, concaving up. We say f is concaving up from negative infinity to negative 1, union with 1 to infinity. And f is concaving down from negative 1 to 1. Of course, those can be inflection points because they're not in the domain. So if I look at concaving down from negative 1 to 1, there's the graph. And concaving up, this is concaving up. And there is no minimum or maximum on the right or the left. And that's pretty much how you determine every possible scenario. Here's a problem again. This is a cosine. We know these graphs are infinite. So domain is all real numbers. Of course, there's no restriction, but we're going to run it between 0 and 2 pi. Intercepts, if I let x equal 0, 0 in there. Cosine of 0 is 1 times a negative, that's negative 1. So on the graph, those are the intercepts. I know the graph crosses, and again, I'm going to expand that a bit. I'm going to make that a 1. So 0, negative 1, the graph is going to go through this point. Now I take a derivative, 1 minus 1 plus the sine of x. Where does that equal 0? That's when sine of x equal negative 1. That happens when x equals 3 pi over 2 plus 2 pi k, but I am bounding the graph between 0 and 2 pi, so there's only one point in that region where this could happen. Three pi over 2. I pick a point to the left, say pi over 2. Sine of pi over 2 is 1 plus 1, that's 2, that's positive. And to the right, say, to the test part, 2 pi. 2 pi is 0, that's 1 plus that, that's also positive. So it seems f is increasing from negative infinity. In our case, we're going to really restrict it from 0 to 3 pi over 2 union with 3 pi over 2 to 2 pi or to infinity, but in this case there it is. Now we take the second derivative test to figure out concavity. The derivative of this will be the cosine of x. Where does that equal 0? Again, that's a special angle. That's when x equals pi over 2 and 3 pi over 2. I do my testing. There's pi over 2. There's 3 pi over 2. There's y double prime. And there's y. I pick a point to the left, say 0. Cosine of 0 is 1. That's positive. Between pi over 2 and 3 pi over 2, well, we know how that works. Between pi over 2 and 3 pi over 2, cosine is negative. And 3 pi over 2 to 2 pi, that's positive. So this is concaving up, concaving down, and concaving up. We have f being concaving up from 0 to pi over 2 union with 3 pi over 2 to 2 pi, and f is concaving down from pi over 2 to 3 pi over 2. We have two inflection points. First inflection point is at pi over 2. You plug that in the original equation. Cosine of pi over 2 is 0, pi over 2. And we have it at 3 pi over 2. Again, cosine of 3 pi over 2 is 0, 3 pi over 2. So keep in mind this is 1.6 about, and this is 4.7. So if I made that 1, I'm going to take that back. I'm going to say that's 1, 2. Of course, you could label that in terms of pi, since everything in terms of pi, if you like. You could say, you know what? Instead of going for 1.6, you could say, well, let's say this is pi over 2. Each 3, right? 1, 2, 3, that is pi. 1, 2, 3, that is 3 pi over 2. And 1, 2, 3, that is 2 pi. So we don't have any maximum or minimums. We have an inflection point at pi over 2, pi over 2. We have another inflection point at 3 pi over 2, 3 pi over 2. Right? And at 0, I am at negative 1. At 2 pi, I could even figure that out. That's 2 pi minus 1. Right? So that would be 2 pi minus 1, which is about right there, let's say. So we have an inflection point right there, and another inflection point right there. And the graph is concaving up. This is concaving up. So concaving up, there it is. And then it concaves down. That's concaving down. And then it concaves up again. And that's concaving up. Oops, not like that. More like this. So there it is. That's the piece of the graph that we're looking for. And that's pretty much it for this section.